Okay, this is Nodal Analysis Lab Part 2. So this is the original circuit, and once you get your measured values, and I decided to use my measured values so this way it might be easier for you to understand how your calculation should look. Now everybody's going to be different. For my V or volts, I use 6.91 volts, and you know that it's set to 1K hertz. So I got my X of C with my my measured value, and my X of C2 with my measured values. X of C1, X of C2. What I did in order to do the calculations on this, I went 6.19 volts divided by 0.998K to get current in parallel with 0.998. So I did a source conversion. Because these two are in series, they will share the same current. You cannot have a node here. So I actually combined those two values so I can do my computed. When I did that, I actually got this. So this is what, so I got 7 milliamps in parallel with the 0.998K ohms. I got my X of C1, X of C2. I put these two resistors together. So now we have a V1 and a V2, okay? Next, I defined my currents, right? I1 is V1 over 0.998K. I2 is V1 over 1.564K at an angle of -90. I3 is V1 minus V2 over this. I4 is V2 over this, and I5 is V2 over this. Now you write your KCLs, and you're going to do entering equals leaving, okay? So what's entering for V1? You got 7 milliamps is entering. I1, I2, and I3 are leaving. Because we usually put I1, I2, I3 in the current, I just kind of swapped them. So now I have I1, I2, I3 plus the current. There's no sign change, right? Because we just swapped it. Now you substitute. You got I1 substituted, I2, and I3 substituted equals the current. The next step is to separate them. Then you put the like terms together. Don't worry about that, if you can even see that. So I put all the V1s together minus the V2 equals 7 milliamps. So that is your first equation for V1. Then I did V2. So here's the equation, and here's the here. So we have entering equals leaving again. So for V2, we have I3 entering, I4 and I5 leaving. So now I kind of moved I4 and 5 over. So I have I3 minus I4 minus I5 equals 0. You substitute I3, I4, and I5. You separate them, and then you put the like terms together. So that was my V2 equation. Okay, once I solved and I put my simultaneous equations in, I got V1 of 3.25 volts at an angle of -2173, and V2 as 512.50 millivolts at -10183. Once you get them, you actually go back to the original circuit, okay? And this area is V1, this area is V2, okay? So basically to get the voltage here, it'd be V1, so it's just the 3.25 volts at 2172. For VC2, you're going from this dot down, so that voltage here is the 512 millivolts, right, at this angle. To get VR1, okay, so now we're looking at this dot, it would be V1 minus 6.91, okay? V2, VR2, would be V1 minus V2, be V1 minus V2 to get that. To get VR3 and 4, you know that they share the same current, so their voltages must add up to V2 voltage. So I got 49 millivolts and 67 millivolts. So that's how you're going to be doing your calculated. Make sure that it's nice and neat. You have your original drawing, because then you have to know you're going to bring back the voltage here and here for V1 and V2 to get your voltage drops. Okay? So, good luck today. Then you're going to do a multi-sim and make sure you use your measured values.